All right, so we're going to think about the squeeze theorem for sine of x over x. And sine of x over x, if we pull up a Desmos graph, looks like this. It's kind of a cool function. It starts off big here in the middle, and then it just gets like closer and closer to the x-axis on the ends, like a little ripple right there. So what we're going to do first is just like, if we're looking as x approaches 0, it's pretty clear from this graph what value that's going to be, right? What value does it look like x approaches as, y approaches as x approaches 0. So as x approaches 0, it looks like you're going to this point right here, and that would be 1. Notice it is undefined at that point, so you can't just plug in 0. You'll get 0 over 0, but it looks like it is 0. However, in math, you can never just like assume that things are the case. Now, sometimes like we know things as accepted facts, and sometimes I will tell you, just trust me. Or most of the time, I'll tell you, just trust me on this. But I do want to give you guys like a little taste of some, of a math degree right here. So, you know, whenever I decided that I wanted to major in math, thought that I would just do harder and harder math problems till I could do every math problem that existed. Not really, but like, I thought, you know, like, those like big long problems that we do that take half a page, I just thought we'd do a bunch of those, like a bunch of different kind of those. And somewhat we did that, like Calc 2 and Calc 3 were mostly that. I had a couple other classes that were like that. What I was not aware of at all were proof classes. And if you major in math, you have to take a lot of proof classes. If you major in math education, you don't have to take as many, but you have to take a few. But at Meredith, they didn't have math education major, so you had to major in math, and your education classes were kind of like a minor that you added on. So, like, I have a actual, real Bachelor of Science in Math, like a real math degree, not a teaching degree. So, I had to take a lot of math theory classes. And I was not prepared for that. I did not really realize what this meant. In fact, let me go dig one too, just to give you a taste of something here that you won't ask me to do this on the AP exam, but I think it is a good thing to do. It's also a good thing to do because whenever you go to college and have professors, especially if you have to take math classes, some of those, I mean, most of these college professors are probably going to have PhDs in math. And they are geniuses. And they want to show you the proofs on everything. So, you know, I try to make things a little more relatable. We do things like Bobo Botno eats DC and the love connection. PhDs in math do not talk about Bobo Botno eats DC very much. So maybe this will be helpful to have at least seen a little bit of it. So, if I were trying to prove that this equals 1, like to say for sure this equals 1, I would first, in this case, if I want to use the squeeze theorem, I would need to think of a function that is always above sine x divided by x, and another one that's always below sine x divided by x. Convenient for you guys, sine x divided by x, if I put cosine in here, you'll notice, now it's not always below, but it's going to be below this for the parts of the graph that matter, right? Because we're approaching 0. So does it really matter what's happening over here, like below -2? Doesn't, right? And above +2? Doesn't really matter there. So this works for the function that's always below. This can be my bottom function, right? Secant x is 1 over cosine x, and secant x is always above this for the part that we really care about, right? Now, in particular, we may want to look at like sort of like some limits to limit this off at. So secant has vertical asymptotes. And it's going to have vertical asymptotes anytime that cosine equals 0. That is at x equals pi over 2 and x equals negative pi over 2. So we got vertical asymptotes there. So I would probably start by just limiting this off to negative pi over 2 to pi over 2, because otherwise the statements that I'm going to make are not necessarily true. So I would say here for pi, what just happened? Oh, I clicked on this. Pi over 2 less than x less than, I'm sorry, negative pi over 2 less than x less than pi over 2. For that to be the case, cosine of x is less than or equal to sine. Okay, I've I linked this and now it's clicking every time I touch where. Let me see if I can fix this so it doesn't do that. I'm going to just take the link off. So next time I do this, I'll probably forget what equations it is. That got rid of all my writing. Sorry about that. Okay. So we'll say 4 negative pi over 2 less than x less than pi over 2. Cosine of x is less than or equal to I took the link out, I thought. Okay, sine x over x, which is less than or equal to secant of x. So, in this case, cosine is always below sine x over x, and secant is always above sine x over x, except at x equals 0, and that is because sine x over x is undefined at 0. So we're putting in that exception right here because of that to be precise in this. Now, in this case, I can find the limit of cosine x. So if I do the limit as x approaches 0 of cosine of x, that is going to equal cosine of 0. And what is the cosine of 0? Unit circle. I think we need to have a unit circle quiz. We're going to have a unit circle quiz soon. Be brushing up on the unit circle. I'll let you know when. It's coming. So be brushing up. I think I got some little ones left over there from last year if you need one. We'll get those later. So cosine, 0 is right here. And coordinates here are 1, 0. Which one's cosine, x or y? It's x. Cosine of 0 is 1. Okay. What functions? Yeah, you would, like, there might be some other functions that you could use for this, these are just ones, I looked up the proof for this, and they're the ones that I found on that proof. So, you know, I also didn't come up with them off the top of my head. It is kind of crazy, like people just like were sitting around thinking about this one day and figured it out. I looked it up. So, and I'm kind of giving that to you, but there might be some other ones that could work for this. Then we also could do the limit as x approaches 0 of secant x. And we might have forgotten, like that's going to be secant of 0. Secant, we don't really know. It's not on the unit circle. What is, what's the equivalent of secant? Nope. 1 over cosine of 0, because there has to be a co with each pair, so secant has to go with cosine. And so cosine of 0 we just found again was 1, and that gives us 1. Sorry. Okay, so we have shown that the limit of the lower function is 1, and the limit of the upper function is 1 at 0. So now we could say, therefore, and did we do the 3 dots some last year? I can't remember. Have you seen me draw these 3 dots in a little triangle? Mathematicians do not like words, so they just come up with symbols so they don't have to write as many words. This symbol right here means therefore. And you can use it, like you can use it on the AP exam. It means therefore. So if you want to cut out some words, you saw on that paper that I passed around, there's like a bunch of upside down A's and little E's and all this stuff. Like all those mean words mostly. So I don't remember what the upside down A is, to tell you the truth, but it meant something. It still does. I just don't know what it is. So therefore, in this case, we can say by the squeeze theorem, the limit as x approaches 0 of sine x over x has to equal 1 also. And so that is concrete evidence for this versus just looking at the graph and seeing that it works. Now, a lot of what we do, just looking at the graph and seeing it works is enough. It's good enough. It's going to get us the right answer. But just to think a little more mathematically here. And, I'll try to sprinkle a little bit of that in. Lots of you are going on to Calc 2 and beyond, so you're going to have to, you might have a math professor that likes to do this sort of stuff. Maybe you'll get a little taste of it so you're not, so shocked by it. Some of you might be interested in a math degree, and you might have some of this in your future. So it's good to get a little bit of taste. The most deceiving class I had to take was, what was the name of that one? It was something like Introduction to Mathematical Reasoning or something like that. This sounded like a baby class. It sounded easy. It was the first proof class you have to take, and it was torture because, you haven't done any of this before. But it sounded like it was supposed to be an easy class. I mean, it wasn't. By the time I finished, it didn't seem that hard. But at the time, whenever they're throwing, this on you and you got to write all these proofs, it was pretty tough. So that is the proof for this. Now that we have proved, however, now that we have proven it, we have proven that this is a fact. So anytime we see the limit as x approaches 0 of sine x over x, we know that it equals 1. So we're not walking through all this stuff again. We just know that that equals 1. So you're not going to have to prove it on any type of quiz or test or anything like that. You're just going to see problems. So let's look at what the problems look like. And they're not that bad. You do need to have it memorized that the limit as x approaches 0 of sine x over x equals 1. So if I look at example 3, I have the limit as x approaches 0 of sine x over 7x. Now that's almost the limit as x approaches 0 of sine x over x. We just have this pesky 7 right here that's in the way, right? So since that 7 is in the way, I've got to think about what I can do with that 7, because if I just have the limit as x approaches 0 of sine x over x, I know that equals 1. Right? So, any ideas? Properties of limits. What's something we could try? Tell your neighbor something crazy you think might would work here. And you cannot, because it's not squared. If it were squared, you could, but all right, any crazy ideas? If it is your neighbor, not yourself, of course, because you would not want to throw crazy out. Any crazy ideas of something we could do? It's a pretty simple step, really. I mean, once you see it, obviously you haven't seen it yet. All right, so can I write this way? Is this still equivalent? Limit as x approaches 0 of 1/7 times sine x over x. That's a 1 right there, but my pen glitched out on me. Is that still equivalent to what I have otherwise? Right? Still equivalent. We multiply it back together, we get the same thing. That would make this right here a coefficient. And properties of limits tell me what can I do with a coefficient. I can pull it out, right? So I can pull this out front. And so now I have 1/7 limit as x approaches 0 of sine x over x. And what is the limit as x approaches 0 of sine x over x? It is 1. We just proved it. 1/7 times 1, we will get 1/7 for our answer. So when you see extra numbers thrown in there that really shouldn't be there, it can usually be pulled out like this. If it's in the denominator, make sure you make it a 1/7, not just a 7. If it's in the numerator, it can usually just be pulled out as a 7. We will see one weird one where there's like a 7 on, or a number on the inside of the sign. We'll see that in a minute there. So here's some options. All right, I realized I did not number these correctly because I went from example 3 to example 5. That should be 4. I probably messed up the whole paper because of that. But so what about over here? There was no rules about tangent x over x, right? And if I try to plug in 0, because I should technically try direct substitution every time. But if I try to plug in 0, tangent of 0 is 0, and the denominator would be 0, and I'd get 0 over 0. So I got to keep going on this. Any ideas? Okay, and what would you change tangent to? Good. So limit as x approaches 0 of sine x over cosine x. This is pulling back some of our favorite stuff, trig identities from pre-cal. So tangent equals sine x over cosine x, so I can do that. And that makes a complex fraction. I'm going to go ahead and put this over 1 right here. And what do I do with complex fractions? Flip the second multiply, so I got limit as x approaches 0 of sine x over cosine x times 1 over x there. Okay, I really need to be doing the limit of sine x over x, right? Because like I know what that is. And I sort of almost have it, right? Because I've got a sine x in the numerator and I've got an x in the denominator. Would it be okay for me to write this limit this way? Can I make it 1 over cosine x times sine x over x? Like if I multiply that back together, do I get the same thing I had above? Right? Because here I just have sine x times 1 on top. Well, here I got sine x times 1. That's fine, right? And then the bottom, I'd have cosine x times x. Here I've got cosine x times x. So it's okay to do this. Like everything's multiplied, so I can switch their order around, right? So that would mean now I'm going to write every step. I'm doing the limit as x approaches 0 of 1 over cosine x times the limit as x approaches 0 of sine x over x, because properties of limits tell me if I'm doing the limit of things that are multiplied together, I can do the limit of those things separately and multiply those things together. And what is our limit as x approaches 0 of sine x over x? We have proven it. It is 1. Over here, I just have to plug in the 0, so I've got 1 over cosine of 0. What is cosine of 0? 1. So that's going to be 1 over 1 times 1. What do we get for our answer here? Just 1 for that. Because of the fact that cosine of 0 is 1, and the limit as x approaches 0 of sine x over x is 1, if you get stuck on one of these problems, 1's a good guess. Like if you can't get it to go anywhere else, guess 1. that is, it's not always going to work, but the answer ends up being 1 for a lot of these. Like the assignment that we usually do with this has lots of 1s and 0s as your answers. So, all right, questions there? Okay. Let's do another special trig limit. Okay, so we need to have memorized the limit as x approaches 0 of sine x over x equals 1. We just need to know that that's the case every time. We also need to know the limit as x approaches 0 of 1 minus cosine x over x here. Let's just type that in. Okay. Similar sort of function, sort of getting skinnier here towards the end. What does it look like our limit at 0 is? Looks like it's 0 for that graph. Probably good enough for us, but what fun would it be just to do that? So let's prove this one. Good. We can prove it using what we've already proved. Yeah, so squeeze theorem is not really going to work well to prove. It might be possible, I'm not sure, but it's not really going to work well. So let's prove it just for the fun of it. We're being math geniuses today, doing extra stuff, preparing us for the future. So is it okay for me to do this? Is that allowed? Okay, as long as I multiply on top and bottom, it's allowed, right? So if I multiply that together, I will get the limit as x approaches 0 of, when I multiply this together, 1 times 1 here gives me 1. I will get a positive cosine x, but I will also get a negative cosine x, so those will cancel each other out, right? I chose, almost like our rationalization, I chose this because it's a conjugate, right? So it cancels out those middle terms, and then I got to multiply cosine times cosine, which is going to give me minus cosine squared x all over x.
On this thing, it says, for example, it says cosine x squared already. Oh, okay. Never mind.
Oh, yes, thank you. I forgot it. Okay, so let's think, what could I do from here? Like that just looks worse, right? It looked like I've made a bigger mess of this. Is there something you see from pre-calc that you're like, oh, we can replace this with something else? What? Numerator. 1 minus cosine squared, what did that equal? It was sine squared. Right, that's like Pythagorean identity. So I can call this the limit as x approaches 0 of sine squared x over x times 1 plus cosine x. And so the only special trig limit I know and have proven right now is that I know the limit as x approaches 0 of sine x over x equals 1. Right? We have proven that one already. Can I do this? Limit as x approaches 0 of sine x over x times sine x over 1 plus cosine x. Is that legal? Okay, I split my signs up in the numerator, but if I multiply them back, sine x times sine x gives me sine squared, so this is still equivalent. And I split my denominator apart, but they're still multiplied together, so it's still the same denominator there. And if I'm doing the limit of two things separately, or two things that are multiplied, I could do those limits separately and then multiply my answers together, right? So I could write this as the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over 1 plus cosine x. And what is the limit as x approaches 0 of sine x over x? It is 1. We have already proven that. And then the limit as x approaches 0 of sine x over 1 plus cosine x, I'm going to use direct substitution on that. It's going to give me sine of 0 over 1 plus cosine of 0. What is sine of 0? It is 0. And cosine of 0 is 1. So this is going to be 1 times 0 divided by 2. And 0 divided by 2 is just 0. And what is 1 times 0? 0. Okay, so we have proven that the limit as x approaches 0 of 1 minus cosine x over x must be 0. So we're just proving things for a little mathematical experience right here. I'm not going to ask you to prove that, although some of those strategies that I'm using show up in the problems, like using those trig identities. But you're not going to be asked to prove it, but you do need to know the limit as x approaches 0 of 1 minus cosine x over x equals 0. That has to be memorized. So these two special trig limits, we have to have those memorized. Okay, are we good here? All right, so let's look at what the problems look like for these. Okay, so we have got the limit as x approaches 0 of 1 minus cosine squared x over x. This one is almost 1 minus cosine x over x, but it's not quite because we have a square right here. So for this, any ideas, something we might could do? I could change it to sine squared x. That'll work. That'll work. I was going to do it differently, but it will work. So I could change that to sine. In fact, I think this is easier than what I was going to do. Sine squared x over x. That's almost sine x over x, and we know that limit, right? So what could I do here? Let's break sine apart. So I'll have sine x over x times sine x. If you want to, you can put a 1 in the denominator there just to keep things lined up really well. You don't have to put it there. Just make sure that sine x is not in the denominator. Still equivalent, right? And then I know the limit as x approaches 0 of sine x over x, and I can multiply it by the limit as x approaches 0 of sine x over 1. So this part right here is 1, because that's the limit that we know. And in this, I'm going to have to use direct substitution, so it's going to be sine of 0 over 1. What is sine of 0? It's 0. And 0 over 1 is just 0, so we get 0. Another really good guess, if you're doing these problems and you can't figure it out, 0 is the other good guess, right? 1 and 0 end up being the answer for a lot of these questions, because by just the nature of one of these being 0 is going to make that happen. So just to give you a glimpse in the other option that I was going to go with, you could have factored this into 1 minus cosine x times 1 plus cosine x all over x, and then you would have had 1 minus cosine x over x, which you can say is 0, and then 1 plus cosine x is going to be 2, but you still get 0 times 2, which is 0. So you could have gone that direction as well, and you would have gotten the same answer. But I actually like what you did better there, Jericho. I think that's probably easier. Although it didn't use our 1 minus cosine x that we just proved there, which is fine. Okay, questions? All right, what do you think about 7? Secant, like we're not going to get anywhere with secant in there, right? We don't know anything about special trig limits with secant. So secant's going to have to be replaced. What could we replace secant with? 1 over cosine. So we're going to do the limit as x approaches 0 of 1 over cosine x minus 1 over x. Oh, this is a good one, because now not only do we have trig, we also have complex fractions. And when we have complex fractions, we want to try to get a common denominator and put that stuff together, right? So the denominator over here is 1. So I could get a common denominator up here by doing cosine x on top and cosine x on bottom. And so that is going to give me 1 minus cosine x all over cosine x. And then the denominator here is still going to be x. And dividing fractions is easy as pie. We can flip the second and multiply. So I'm going to go over as far as I can this way because I'm running out of room. Limit as x approaches 0 of 1 minus cosine x over cosine x times 1 over x Do you guys see a special limit sort of built in here? One of the two that we know for sure. One of them was sine x over x. That's not here. We don't have sines. The other one was 1 minus cosine x over x. It's like right here, right? I could rewrite this in a different way. So I could do limit as x approaches 0 of 1 minus cosine x over x times the limit as x approaches 0 of 1 over cosine x. And that special limit 1 minus cosine x over x, that gives us 0. Right here we would use direct substitution. We're going to get 1 over cosine of 0, which is 0 times 1 over 1, and that is going to give us 0 there also. I feel a little disappointed to do all that work and get 0 as the answer like over and over again, but it happens a lot just because of the nature of the number 0. Whenever you're multiplying something by 0, it's going to give you 0. Okay. Questions? All right, here's the last one that we're going to do. So, for this one, it looks a lot like that very first example we did where we had the 7x in the bottom. And so it looks a lot like we could just like pull that 4 out, right? But this 4 is inside of those parentheses. Is it a legal move for us to just like take the 4 and pull it out? It is not. So, we're going to have to do something a little bit differently here, or at least think about this a little bit differently. So, my limit as x approaches 0 of sine x over x equals 1. But it is also true as long as whatever you have right here matches whatever you have right here. So it would also be true, like if I did the limit as x approaches 0 of sine of 4x over 4x, that would still equal 1. So as long as what you have inside of your parentheses matches the denominator, that would still equal 1. So what I really want to do is I just want to like put 4 right there. That'd be nice, right? Get 1. But is it legal for me to put a 4 there? No. But I could put a 4 there if I do something else with it. What else would I have to do? If I put a 4 in the top, then this 4 and this 4 cancel each other out. It's really just 1, so I haven't changed the value of anything here. So I could write it this way. The limit as x approaches 0 of 4 times sine of 4x over 4x. If you want to, you can put that 4 over 1. Which means I've got the limit as x approaches 0 of 4 times the limit as x approaches 0 of sine of 4x over 4x. What is the limit as x approaches 0 of sine of 4x over 4x? It's just 1. What's the limit as x approaches 0 of 4? It's 4. You don't have anywhere to plug in that 0. So it's just 4, and we would get 4 as our answer. Now, here's the thing about this. I told you that you could not just take the 4 and pull it out, right? And you can't. That's not a legal move. If you have to show work on this, you can't do it. If you took the 4 and just pulled it out, would you get the right answer? Yeah, you would. So, like, the wrong thinking could still get you the right answer on this problem, and more or less would work every time if you had the 4 there. So it's not good to think about pulling that 4 out, but it does kind of work like you're pulling the 4 out for that. Okay. Do make a special note in your mind. These special limits are at x approaches 0. If we've got x approaches 1 of sine x over x, direct substitution, totally different problem, right? For this. So what we're going to do right now is I'm going to come around and check the homework that you had last night. And I'm going to have you guys do a few more problems. This is not going to be tonight's homework. We're going to do a different thing for tonight's homework. So we're just going to take a little bit of time right here in class to do these, and then we'll go over a few of them. So let me make sure, let's see if this is really what I want you to do. We're not going to do this like 97 and 101 one. There's squeeze theorem problems, and we're gonna do some squeeze theorem stuff on a different assignment, so you don't have to do those. So right now, I want you to take some time and try 69 through 78. And I'm